The topic is rational functions and multiplying and dividing rational expressions. The first objective in this topic is finding the domain of a rational expression. So what is a rational expression? A rational expression can be written in the form P over Q, where P and Q are both polynomials and Q is not equal to 0 because Q is on the bottom of a fraction looking thing that's dividing by Q. We can't divide by 0. So this is just like a rational number. A rational number is P over Q, where P and Q are integers. Here we're just saying that the numerator is an expression and the denominator is an expression. So some examples. 3x squared plus 2x minus 4 over 4x minus 5. Polynomial on top, polynomial on the bottom. That's a rational expression. 4x plus 3y over 2x squared minus 3xy plus 4y squared. Polynomial on top, polynomial on the bottom. That's a rational expression. 3x squared over 4. 3x squared is a polynomial. 4 is a polynomial. This is a rational expression. Let's look for the domain of each rational function. We find the domain, in other words, what we can have for x, by first finding what we can't have for x. And in a rational expression, what we can't have is 0 on the bottom. In A, there's no way to get 0 on the bottom. There's no variable in the denominator with that 3. So the bottom will always be 3. It'll never be 0. There are no restrictions on A. So the domain would be the set of all x such that x is a real number. We do have a restriction on B. X minus 1 could possibly be 0. And if we set x minus 1 equal to 0, we get x equals 1. So the domain, what is allowed, would be the set of all x such that x is a real number and x is not equal to 1. C. Similarly, the bottom of C can be equal to 0. So we set x squared minus 2x minus 15 equal to 0. We'd have to factor. And when we factor, we get x minus 5 times x plus 3. And when we solve, we get x equals 5 and x equals negative 3. So those are the values that would make the bottom of this rational function 0. Those are the values that are not allowed. So the domain, what is allowed, would be the set of all x such that x is a real number and x is not 5, x is not negative 3. Notice it looked like we had a fraction. An expression that has a fraction in it looks like it has a numerator and a denominator, but it is a single expression. That is called a rational expression. Just like a rational number is a number that can be written like a fraction, a rational expression, notice root word ratio, also looks like a fraction. And if we use rational expressions in an equation, that is, if we start putting equal signs in there, then we have rational equations. Let's take a look at x over x minus 3. This is a rational expression because we see it's written
as a fraction. It has a numerator, it has a denominator. What would be the value of this rational expression if x equaled 6? So if x equals 6, what would be the value of this rational expression? We can figure that out by plugging 6 in for x. If x is 6, then we have 6 over 6 minus 3, which is 6 over 3, which is 2. So if x is 6, this expression is 2. What about if x was negative 3? If x was negative 3, we would have negative 3 over, careful with your signs, negative 3 minus 3. This would be negative 3 over negative 6. Negative divided by negative is positive. This is positive 1/2. So if x is negative 3, this expression would have a value of positive 1/2. We found that by plugging negative 3 in for x. What about if x was 0? If x is 0, what's the value of this function? Well, notice that makes the top 0. And even though on the bottom we would have 0 minus 3, since it's 0 over a number, that means it's just 0. 0 divided by anything is 0. So 0 on the top, that's okay to have. It gives us 0. What about, let's do this one final time with this same expression, x over x minus 3. What if x was positive 3? Well, that would give us 3 over 3 minus 3, which would be 3 over 0. Uh-oh. 0 in the bottom of the fraction, dividing by 0. That's undefined. Which means if x is 3, we don't have a value for this expression. So 0 on the top, that's okay. That just gives us 0. 0 on the bottom makes it undefined. These numbers that are going to cause our rational expressions to be undefined are going to be called restricted values. So what are restricted values? Restricted values are values for x that cause our expression overall to be undefined. What causes things to be undefined? Well, denominators being 0, the bottom of a fraction being 0, divided by 0. So the way we can find our restricted values is by taking the denominator of the rational function, in this case, x minus 3, and let's set it equal to 0. Add 3 to both sides, we get x equals positive 3. So x equals positive 3 is a restricted value because it causes overall the bottom, the denominator, to be equal to 0. Let's find some more restricted values. if we had x minus 7 over 3x plus 5, what would be the restricted value? Well, we find these by taking the denominator, 3x plus 5, and setting it equal to 0. Subtracting 5 from both sides, 3x equals negative 5. Dividing both sides by 3, x equals negative 5/3. So x equals negative 5/3 is the restricted value. Plugging in negative 5/3 for x causes us to have 0 on the denominator. What would be any restricted values of negative 5 over 3x squared plus 6x? What would be the restricted values? Well, it would be what we get when we take the bottom, 3x squared plus 6x, and we set it equal to 0. We have a quadratic. What do? Everything on one side, 0 on the other, factor, and solve. Everything is on one side. We do have 0 on the other. So let's factor. 3x squared and 6x. We have a common factor of 3x. Our leftover piece would be x plus 2. 3x times x is 3x squared. 3x times positive 2 is positive 6x. Factor and solve, because we could use the 0 factor property. Either 3x equals 0 or x plus 2 equals 0. Divide both sides by 3, we get x equals 0. Subtract 2 from both sides, we get x equals negative 2. These are both the restricted values of this expression. They are the values that will cause us to have 0 in the denominator. Let's do restricted values again. Let's find the restricted values for the expression 3x over x squared minus 7x plus 6. So restricted values are what we get when we set the bottom equal to 0. It's a quadratic. Everything on one side, 0 on the other. Factor and solve. We would need the two numbers that multiply to positive 6 and add to negative 7. These two numbers would be that multiply to positive 6 and add to negative 7. That's going to be negative 6 and negative 1. Those aren't the restricted values. Those are the numbers we're using to factor. Go ahead and take each factor and set it equal to 0. X minus 6 equals 0. X minus 1 equals 0. Add 6 to both sides, we get x equals 6. Add 1 to both sides, we get x equals 1. Positive 6 and positive 1 are the restricted values. Positive 6 and positive 1 are the numbers that if we plug them in for x, they will give us 0 on the bottom, which makes it undefined. Restricted values again. We have a plus 10 over a squared minus 25. What are the restricted values? Well, the restricted values are what we get when we set the bottom equal to 0. Now, 2 ways to solve this that we know about. We could factor and solve. As a difference of squares, this would be a plus 5 times a minus 5. Set both of those equal to 0 and solve to get a equals negative 5 and a equals positive 5 as the restricted values. But you could also use the square root property here because we just have a square term and a constant. We can easily get the square on one side and everything else on the other, so we can do square roots of both sides. Be careful if you do it this way that you remember a plus or minus 5. A equals positive 5 or negative 5. When we take square roots of both sides of an equation, we have to remember the plus or minus. So one way or another, we would set the bottom equal to 0 and solve to get a equals positive 5 and a equals negative 5 as the restricted values for this expression. It's about time that something fun happened, relatively speaking. 2x cubed plus 5 over x squared plus 9. Well, to find the restricted values, which is what we are still doing, we would take the bottom, we would set it equal to 0, and we would solve. There is no way to factor a sum of squares. If this was x squared minus 9, we would do x plus 3 times x minus 3. We would be on our way. But we can't factor a sum of squares. A sum of squares is prime. If we went and used the square root method, we would get x squared equals negative 9. And we know now with complex numbers, x would be plus or minus 3i, the square root of a negative number. But when we're talking about restricted values, we're talking real number system only. So while we know that with complex numbers, we can do I, when we're talking about the things that we can and can't have for x, those are real numbers only. And in the real number system, we cannot take the square root of a negative number. That means we have no solution. That means we have no restricted values. There are no values of x that would cause this to be undefined. And let's look at this, because that does make sense. When we square something, it's going to be positive. The smallest number we can have is 0, because if we plugged negatives in, a negative squared is a positive. So 0 squared would be 0. That's the smallest we could have for x squared. But then we add 9. So the smallest that the bottom of this fraction could possibly be is 9. It can never be 0. So there's no restricted values. There's nothing that can make the bottom 0. And when we try to set it equal to 0 and solve, we would get no solution because of that, because it's not possible to have 0 on the bottom here.
Objective 2 in this topic is simplifying rational expressions. Simplifying a rational expression means writing it in lowest terms or simplest form, just like simplifying a fraction. Why do we focus on fractions in early math? It's because eventually you're going to get to rational expressions and they all work the same way. The fundamental principle of rational expressions. For any rational expression P over Q and any polynomial R where R is not 0, P times R over Q times R is the same as P over Q times R over R, which is the same as P over Q times 1, which is just P over Q. In other words, if there's a common factor to the top and the bottom, we can cancel that common factor away. PR over QR is the same as P over Q. We can cancel away the R. So the steps to simplifying a rational expression in lowest terms. First, we completely factor the numerator and completely factor the denominator of the rational expression. Then divide out common factors to the numerator and denominator. This is the same thing as removing the factor of 1. That doesn't change the value of the expression. A word of warning, only common factors can be eliminated from the numerator and denominator. So make sure any expression you eliminate is a factor. Make sure you're not eliminating things that are separated by plus. Those are terms. As an example, let's simplify the following expression. X squared plus 3x minus 4 over x squared minus x minus 20. Why is this topic paired with factoring? Because you need factoring to be able to succeed in this topic. We need to factor the top completely. We need to factor the bottom completely. On top, we need numbers that multiply to -4 and add to +3. That's +4 and -1. On the bottom, we need numbers that multiply to -20 and add to -1. That's -5 and +4. So in factored form, we have x plus 4 times x plus 1, times x minus 1, over x minus 5 times x plus 4. The x plus 4s cancel, leaving us with just x minus 1 over x minus 5. That word of warning before, make sure what we're factoring, or make sure what we're canceling are factors. Some people might look at x minus 1 over x minus 5 and attempt to cancel the x's. We can't cancel the x's. The x's are not factors. The x's are terms. Let's simplify the following expression. We have a bit of a trick here with 7 minus y over y minus 7. The trick is when we have the same thing on the top and the bottom, but it's not really the same. They're both minus, and the terms are switched around. 7 minus y on top, y minus 7 on the bottom. We can get them to be exactly the same thing if we factor in -1 out of one of them. If we factor in -1 out of the top, the leftover would be y minus 7. How come? -1 times y is -y. -1 times -7 is +7. -y plus 7 is the same as 7 minus y. So these are equivalent. This is what we get when we factor out a -1. Now that we've written it with that factor of -1, now that we see a y minus 7 and a y minus 7, we can cancel. Before, we couldn't cancel. They weren't the same thing. But now that we can, the y minus 7's cancel, leaving us with just -1. An opposite over an opposite is -1. Let's simplify x cubed plus 8 over x plus 2. Factor the top, factor the bottom. Well, the bottom can't be factored, but the top is the sum of cubes. That's the SOAP formula. Same, opposite, always plus. The two things being cubed are x and 2. So that factor that gets created when we factor the sum of cubes, that x plus 2, cancels with the x plus 2 on the bottom. The rest of the factorization, x squared minus 2x plus 4, the x squared, the x times the 2 squared, with the opposite and the always plus, the minus and the plus. That remaining piece is actually our answer. It's all that's left. Two y squared plus 2 over y cubed minus 5y squared plus y minus 5. On top, we can factor out a 2. We'd be left with y squared plus 1. That can't be factored any further. There is no factorization for the sum of squares, just for the difference of squares. On the bottom, we would factor by grouping. Group the first two, the y cubed minus 5y squared. Group the last two, the y minus 5. We can factor out a y squared from the first two, leaving us with y minus 5. We'd write in our plus 1 so that we don't miss that the leftover piece when we factor out the common y minus 5 is going to be y squared plus 1. That y squared plus 1 on the bottom cancels with the y squared plus 1 on top, leaving us with just 2 on the top and y minus 5 on the bottom. So factor the top, factor the bottom, cancel common factors. Your answer is what's left. So when I teach fractions, I make a point of saying, hey, it's real important that you learn these rules for adding fractions, for subtracting fractions, for multiplying them, for dividing them, for reducing them. Because down the line, you're going to have to know how to do all those things with rational expressions instead of just the fraction 2/3
fractions that have expressions on the top and expressions on the bottom. And here we are. So our path is going to be a lot like the path for learning how to work with fractions. We introduce numerator and denominator. With rational expressions, the denominator can't be 0. That's a little more interesting in expression land, because in number land, dividing by 0 can only look like a 0 on the bottom. But we started working with these expressions. So instead of just saying, hey, watch out for a 0 on the bottom, this turned into a whole discussion about restricted values, which give us restricted values give us 0 on the bottom. So what did we learn about with fractions next? Well, after we introduce what a fraction is, we start talking about reducing fractions. So just like we simplify fractions, let's work on simplifying rational expressions. Let's say we had (2x cubed) plus 12x squared plus 16x all over 6x plus 24. Well, the thing you absolutely cannot do is go, oh, 2 over 6, that's 1/3. You can't go, oh, 12 over 6, that's 2 over 1. You can't just pick something from the top and pick something from the bottom and cancel them away. Not when it's written like this. If we had the fraction 4/8, it's because of the fact that this is 4 times 1 over 4 times 2 that we can cancel the 4s and be left with 1/2. It's because when it's all written as multiplication, that's the key. When it's all written as multiplication, something times something times something times something all the way across. Then we can cancel common factors. There's no such thing as canceling common terms. It's common factors. That same thing's at play here. So we just can't pick this term and decide, hey, let's cancel those. It doesn't work that way. In fact, if it helps you to think about, this is like having 2x cubed over 6x plus 24 plus 12x squared over 6x plus 24 plus 16x over 6x plus 24. How do we add 3 fractions with a common denominator? Well, when it's the same thing on the bottom, we leave it on the bottom and then we add across the top. So that's why we can't just make this 6 go away if we cancel it with the 12, because that 6 still exists as a part of the front and the back. Only by writing everything as multiplication, only by writing everything as factors can we reduce. And that's why we just learned how to factor. So let's factor the top. Let's factor the bottom. What's the first step in factoring anything? That's right. See if we can factor out a greatest common factor. On the bottom, 6x and 24, we can factor out a 6. We're left with x plus 4. On the top, we can factor out 2x. And what are we left with? We're left with x squared, because 2x times x squared is 2x cubed. 2x times positive 6x would be positive 12x squared. And 2x times positive 8 would be positive 16x. And this factors further. So if we wanted to factor x squared plus 6x plus 8, x and x, we would need numbers that multiply to positive 8 and add to positive 6. Those numbers are positive 4 and positive 2. So completely factored, the numerator here would be 2x times x plus 4 times x plus 2. The denominator would be 6 times x plus 4. Now, we're not done. But before we take the next step, I want to take a moment and talk about the restricted values. In a problem that has a bunch of factoring like this, since the common thing we do to find the restricted values, we set the bottom equal to 0 and solve, it becomes much easier and something that we're likely going to do anyway to make sure the bottom is completely factored. And then we can find our restricted values. So along the way here, we ended up factoring the bottom completely. We got 6 times x plus 4. And if we set that equal to 0, we get 6 equals 0. We get x plus 4 equals 0. 6 plus 0 is absolute nonsense. X plus 4 equals 0. We subtract 4 from both sides. We get x equals negative 4. So x equals negative 4 is our restricted value. Why did I just pause the problem, which, by the way, was write this in simplest form? Well, it's because that factor that we got the negative 4 from, that x plus 4 that we set equal to 0, that we must set equal to 0 to find out that it's a restricted value, that factor just canceled away. So we got to find it here at the beginning of the problem, because by the end of the problem, that information might not be there anymore. We could also reduce now the 2 over the 6 to 1/3. 1/3. And 1 times x is just x. So what we have here is x times x plus 2 all over 3. This and this are the same. But actually, I'm going to uncircle this for a second. There are some restricted values, like this one, that we must name. So this here, the original problem, the original expression, is equal to this, provided that x is not -4. And we explicitly say that because it came from a factor that canceled. Could we look at, let me erase everything here except the original problem and the answer. Can we look at this and know, without it being said, that x can't equal -4? If all we saw was the x times the x plus 2 over 3, we would take the bottom, we would set it equal to 0, and then we would solve to find restricted values. 3 equals 0 is nonsense. So we would come away thinking there are no restricted values. And if we plug -4 in to x times x plus 2 all over 3, we get -4 times -2 all over 3, positive 8/3. We get an answer. But if we plug -4 into the original version, 6 times -4 is -24. -24 plus 24 is a big ol' honkin' 0. -4 makes this thing have a 0 on the bottom. -4 is undefined. When we reduce this expression to x times x plus 2 all over 3, since that information is not visibly explicit to us anymore, we have to say, hey, don't make x -4. That value you get, that positive 8/3, that's a lie. You don't get 8/3 if you plug it into the original. And what's the whole deal about reducing fractions? 4/8 reduces to 1/2. They are equivalent. In every sense of the word, 4/8 equals 1/2. So you can't say this equals that, except for that one time where if you plug it in here, it's undefined, and you plug it in here, it's positive 8/3. We can't have any of that. So we say x can't equal -4. If you're confused, I promise you I didn't do so much there. I just talked a lot. We're going to do another example right now to drive this point home, show, hey, if I know how to find restricted values, if I know how to factor, I can reduce rational expressions. In fact, when you think about it, what we're doing isn't really all that new. You know how to reduce fractions. You know how to factor. Now we're factoring to reduce fractions. That's all. Let's reduce x squared plus 3x minus 28 all over 2x plus 14. 2x plus 14. Well, if I factor the top and I factor the bottom I can factor out a 2. I'm left with x plus 7. On the top, I need two numbers because this is going to be an x times an x. I need two numbers that multiply to -28 and add to +3. These would be +7 and -4. They multiply to -28. They add to +3. So in goes a +7. In goes a -4. Now I've completely factored the top. I've completely factored the bottom. Before I cancel, I look for my restricted values. I take my factored form on the bottom. 2 times x plus 7. I set that equal to 0. I get 2 equals 0. I get x plus 7 equals 0. What is 2 equals 0? Nonsense. That's right, it's nonsense. Here, subtract 7 from both sides. X equals -7. This is my restricted value. It's going to be important that I found that because it's coming from the x plus 7 factor, which is gone. So this completely reduces to x minus 4 over 2. And since we can't see that x plus 7 factor on the bottom anymore, we have to say, hey, x cannot equal -7. Make sure here, since it's a restricted value, we're saying x cannot equal that you're using the not equal sign. In fact, if you want to go through and put it there, you can. I don't do that though, because I don't want to accidentally get confused. When I come over here, I go, hey, 2 equals 0. That's nonsense. If that said 2 doesn't equal 0, I might forget to say that's nonsense. So I find my restricted values. I just remember that when I write it here, we have a not equal sign. So remember when we worked on the exponent rules. Our next example is not a new problem. 2 over 8 is 1/4. We can keep it all together, play how many more where. For the x's, how many more where? We have x to the 4th on the bottom, squared on top. That's 2 more on the bottom. For the y's, how many more where? I got 5 more on top. That's a y to the 5th on top. 1 times y to the 5th is just y to the 5th. 4x squared on the bottom. Is there any restriction we should name here? Well, since originally we had a factor of y on the bottom, That means that y can't be 0. We can still see that x shouldn't be 0, but we can't see that y isn't 0 anymore. So I'm going to go ahead and say y can't be 0. And I'm going to make that part of the answer. The book mentions it. Doesn't make a point of putting it with the final answer here. I would. Again, simply because here in the original version of the problem, we can clearly see y shouldn't be 0. That would cause a big issue. So y being 0 needs to cause that same issue at the end. Since it doesn't, we go ahead and add that in. So I had played the how many more where game, but again, we can have gone 2/8. That's 1/4. And then x to the top minus bottom, 2 minus 4. Y to the top minus bottom, 8 minus 3. That's 1/4 x to the negative 2, y to the positive 5th. Negative exponents go on the bottom, so to the bottom with the 4. And the y to the 5th will come up top. It's times the 1. And again, you can say y cannot be 0 there. Next up, t cubed plus 8 over t squared plus 4t plus 4. Let's go ahead and factor the top, factor the bottom. On top, this is a sum of cubes. We can use that SOAP formula. For the sum, for the plus, same as the plus, opposite of the plus, always plus. Our two things that are being cubed here. This is t cubed plus 2 cubed. So t and 2. T squared, multiply them together, 2t, square the 2, 2 squared is 4. Square the first, multiply them together, square the second. On the bottom, this, if you're following the, I don't want to call them rules, but if you're following the step-by-step how to factor anything, we've got factor out a greatest common factor. We don't have that. Ask yourself, is it 2, 3, or 4 terms? On the top, it was 2 terms. It was a sum of cubes. We factored appropriately. On the bottom, it's 3 terms. You should, at that point, ask yourself, is it a perfect square trinomial? In this case, it turns out, why, yes, it is. This is what we get when we square t. This is what we get when we square 2. And 2 times 2t is 4t. It was a plus here, so this is t plus 2 quantity squared. But it's okay if you didn't ask yourself if that's a perfect square trinomial. If you didn't factor it, using the special formula, you would just be looking for two numbers that multiply to +4 and add to +4. Those numbers would be +2 and +2. T plus 2 times itself is t plus 2 squared. Since t plus 2 times itself is t plus 2 squared, for the sake of the visual, let me write it that way. The visual being, I'm going to cancel that. So we're left with t squared minus 2t plus 4 over t plus 2. Now, it is only because of the fact that we still have that t plus 2 left over that we didn't have to say, and by the way, t can't be -2. Because, yeah, our restricted values is actually only one restricted value, a t minus 2 that we get twice. So even though one of those got canceled away, we were still left with the other one. So we can still look at our answer and see, hey, t can't be -2. And because we still see that information, we don't have to say it. And I said, for the visual, I'd show it that way. But if we had a t plus 2 squared on the bottom and a t plus 2 on the top, canceling one of them on top is canceling one of the factors on the bottom. Just like x over x squared would end up 1 over x. How many more where? One more on the bottom. T plus 2 over t plus 2 squared. When the t plus 2's go, it still leaves us with one factor on the bottom. So lots of ways to write the factored step, the cancellation there. But in the end, you'll have t squared minus 2t plus 4 over t plus 2, no restriction needing to be written. Let's do another just like this. Let's take a look at p cubed minus 27 over p squared minus 6p plus 9. When I said just like this, I wasn't kidding. The bottom is a perfect square trinomial. This is p minus 3 squared, actually. This is what we get when we square p. This is what we get when we square 3. This is what we get when we multiply them together and double. 3p times 2 is 6p. That's what makes it a perfect square trinomial. That's why we can make it p and 3 squared, and the minus is why it's a minus here. On top, p cubed minus 27 is a difference of cubes. The two things being cubed are p and 3. Set up our SOAP formula. We're starting with subtracting 2 cubes. So same as the minus, opposite of the minus, always plus. P and 3, p squared, 3p, 3 squared. 3 squared is 9. The factor of p minus 3 on top cancels with one of the factors of p minus 3 on the bottom. p squared plus 3p plus 9 over p minus 3. It's as simplified as we can take it. We don't need to explicitly say p can't be 3 because we can still see that information. Since we can still see a p minus 3 factor on the bottom, that tells us that p can't be 3. We don't write it again.
The third objective in this topic is multiplying rational expressions. So the rule for multiplying rational expressions is the same as the rule for multiplying fractions. P over Q times R over S is PR over QS. Multiply across the top, multiply across the bottom. Our fractions rules coming back around yet again. And we have the note as long as Q isn't 0 and S isn't 0, because we can't have 0 on the bottom of a fraction. We can't divide by 0. So the steps are completely factor each numerator and denominator, and then use the rule above, multiply the numerators, multiply the denominators. Finally, simplify the product by dividing the numerator and denominator by their common factors. So let's multiply the following rational expressions. M minus n squared over m plus n times m over m squared minus mn. Well, let's write out that m minus n squared is m minus n times m minus n, and then we would be multiplying that by m. And then we factor the bottom right, m squared minus mn, we can factor out an m to get m times m minus n. That's multiplied by the first denominator, m plus n. It looks like we can cancel an m minus n, and we can cancel an m. That leaves us with m minus n over m plus n. So factor everything and multiply across the top, multiply across the bottom, then cancel common factors. What we're left with is the answer. Just like multiplying fractions.
Anything over itself is 1. 3 over 3 is 1. Negative 4 over negative 4 is 1. This also means anything over its opposite is negative 1. Negative 3 over 3 is negative 1. 3 over negative 3 is negative 1. Why? Well, because anything over itself is still 1, but when we have two different signs, that makes it negative. If we expand this to rational expressions, anything over itself is 1. So x plus 2 over x plus 2 is 1. And because we can add in any order, x plus 2 over 2 plus x would also be 1. Because x plus 2 is the exact same thing as 2 plus x. Now, that doesn't hold up with subtraction. Now, anything over itself is still 1. X minus 2 over x minus 2 would be 1. But it's a completely different story if we have x minus 2 over 2 minus x. What happens when we subtract two numbers in a different order? Well, again, adding 2 plus 3 is 5, 3 plus 2 is 5. Adding it doesn't make a difference. Subtracting 3 minus 2 is 1. 2 minus 3 is negative 1. 6 minus 4 is 2. 4 minus 6 is negative 2. So if we switch the order of subtraction, we get opposites. A number divided by its opposite, well, we just talked about how that's negative 1. So when we have the same order but flipped, so I guess when we have the other order, when we have the same numbers but flipped order with subtraction, that equals negative 1 overall. What's another way of writing a number and its opposite? Well, if x is a number, then the opposite of x would be written negative x, which is a little confusing because sometimes negative x is not a negative number. If x was already negative, this would actually be positive. So I try to remember to say x and the opposite of x, but I'm going to say minus x. I'm going to say negative x. These are how we talk about these things. If the number is x plus 2, then the opposite of x plus 2 could also be written as negative x minus 2. I'm distributing that negative sign. So x plus 2 over negative x minus 2, that's a number over its opposite. X plus 2 over negative x minus 2 would be negative 1. Why am I pointing this out? Well, here's our next example. X minus 5 over 25 minus x squared. Let's simplify this rational expression. Well, that's x minus 5 on the top, and the bottom is going to factor, since it's a difference of squares, to 5 plus x times 5 minus x. We can't actually cancel x minus 5 and 5 minus x unless we cancel them and leave over a negative 1. Then this would become negative 1 over 5 plus x. From that canceled factor of 5 minus x, there was some information there. 5 minus x can't be 0. So negative x can't be negative 5, and x can't be positive 5. Positive 5 being plugged in for x is the thing that makes that factor 0. We don't have that information at the end. X can't be positive 5. X also can't be negative 5, but we still see that at the end. Don't worry too much about, do I put it, do I not put it? I'm writing it to be complete. Unless the problem is specifically asking you for a restricted value, don't worry. The important thing is that you can reduce it to here, which could also be -1 over x plus 5, because we can add in either order. 5 plus x is the same as x plus 5. So again, we need to be able to recognize that x minus 5 over 5 minus x is -1, that it's something over its opposite, because then we can cancel them away and leave a -1 behind. I want to show another way to think about this. It still requires you to recognize, and you better recognize, so let's bring it all the way back to, hey, we factored the bottom, we got 5 plus x times 5 minus x. We can't cancel these, but I can multiply by anything over itself. I can multiply by 1. 1 is anything over itself. I can multiply both the top and bottom by -1. But I'm only going to multiply it through down here, because I want to flip one of them. So on top, I have -1 times x minus 5 still. I'm just switching the order. On the bottom, I have 5 plus x times, well, what happens if I multiply this by -1? That's -5 plus x, or x minus 5. X plus -5 is x minus 5. Multiplying a -1 through one of them is going to switch it around. And then we can just cancel normally, and we can see we're left with -1 over 5 plus x, or -1 over x plus 5.